What up? Today we're going to talk about 2.5 through 2.8, which has a lot to do with exponential stuff, has a lot to do with, as you can see, inverses. What is that? Some composites. Let's just get right into it. We're going to talk about exponential modeling first. Okay. Now, an exponential function is in the form f of x or y equals a times b to the x. Now, if b is positive and greater than 1, you have what's called exponential growth. Now, the reason why I said positive and greater than 1 is because I'm preparing myself for this next guy. If b is positive and less than 1, in other words, between 1 and 0, you have what's called decay. Now, exponential growth is going to look like this. Exponential decay is not going to be the flipped version of it, but it's going to look like this. Now, what does A have to do with it? A has to do with how stretched out it becomes or skinny it becomes. The larger the number, the faster it goes up. The larger or the smaller the A, the longer it takes to go up. If A is negative, then you're looking at this guy getting flipped upside down and that guy also getting flipped upside down. So A kind of determines, very much like when you were doing with horizontal shrink, okay? Pretty much the same exact idea, where if you were to multiply a number to the entire f of x, which is kind of what we're doing here, it makes things skinnier and wider. Now, what's also important to note about exponential modeling is when I graph these guys, okay, they all level out at some point to 0. So growth looks like that. Decay looks like that, where everything seems to level out to 0. Okay, and that's going to be your range. Once I manipulate A or add a number, that's when things shift and things change, but we'll get there when we have to get there. Exponential modeling. Okay, modeling, something I did a ton of in college. Now, composite functions. Okay, a composite function can look one of two things. If I give you something like g of f of x, okay, that means you're going to take f of x and plug it into g. I could also write that out as golf, which is a sport. So, if I were to look at something like this guy right here, okay, and if I were to be like, what is f of, I'm literally making this up, f of g of 1. And if I were to look at this picture right here, I would say, okay, well, let's do the inside first. Let's do the inside, most interior part. G of 1, according to this, is 3. All right, so this is saying find f of 3. X is 3. F of 3 is now negative 2.5. So it's a two-step process for you to get a final result. Now, I believe I created these to be the same exact thing. So, I could also plug stuff into one thing and get the other. That would work just fine. But I'm going to wait to do that until I get to a bunch of examples because I don't want to overdo it beforehand. I think I have like a lot of slides on here. I don't want to do too much. Okay, not yet. Inverse functions. Now, I actually am going to do it right here. Two things to know about how to find an inverse function, and let me just do one of them. Let me do the uglier one, g. This is how you find the inverse, okay? So I'm going to call that y, just to make my life a little bit easier. Whenever you're being asked to find an inverse function, step number 1 is flip the x and the y, okay? So I'm going to make that look like x equals 4y squared minus 1. That's step 1. Step 2 is you're going to solve for the new y. So you add 1 to both sides. So x plus 1 equals 4y squared. Divide everything by 4. So you have y plus 1 over 4 equals y squared. And in this case, you square root both sides. Don't forget to attach your positive and negative whenever you're square rooting. So that gets me positive or negative square root of x plus 1 over the square root of 4, which is 2, equals regular y now. The last step, second to last step, let's flip this and make it look prettier. Y equals positive or negative x root x plus 1 over 2. And the last thing you're going to do is you're now going to call it the inverse, which looks like that. Now, that's important thing number one. That is how you deal with it analytically or algebraically or however you want to view that. Now, the way you would deal with this from a graphical point of view is if I asked you to graph that, okay, if I asked you to graph G, no big deal. G is going to look something like this. Something like that. Now, the graph of an inverse is you drawing out the perfect equation y equals x and you reflecting it over y equals x. So basically what happens is the reflection is going to show up that way. So this guy is now going to look something like this. Definitely not an exact thing, but what it is if you were to take that black dotted line and fold it over, okay, the two graphs are going to fold onto each other. Okay, so that's how you look at an inverse graphically. Can you draw that dotted line there and fold it over? In this case, yes, even though I'm a terrible artist. And if I wanted to find it algebraically, that's how you found it algebraically. So, can I do problems now? No. This is very important. This is something that I, for whatever reason, struggled with up until pre-calculus, but it's not that bad. A residual plot is if I give you a bunch of data. If I'm like, hey, look at this information. If I'm taking like the temperature over the course of a couple days and I use that temperature and I create a line of best fit, not every single dot is going to hit that line of best fit perfectly. Some dots are going to go above and some dots are going to go below. A residual is how far above or below your value is compared to the line of best fit. So if I were looking at this and, if I were to use this as a real life thing, at x equals 0, I get 2. 2 lives above my line of best fit. This guy lives above my line of best fit. This guy lives below my line of best fit. But I should be able to look at this and say, yeah, all right, so my dots don't fit this line perfectly, but is the linear equation that I created here good? Yeah. And here's how I can determine that. Okay, this is what a residual plot looks like. A residual plot is if you were to take your line of best fit, make it horizontal, so like tilt it to the side, and look at the dots above and below. Now, I'm going to, can I clear it? I can't erase. It won't let me erase. Nope. So basically, a residual plot looks like this. Do I have a picture over here? No, I don't. So if I were to look at just this guy right here, ignoring these lines, I have a dot above, a dot above, a dot below, a dot below, a dot on, above, below, below. There's no pattern. There's no obvious pattern that's going on with my residual points. If you don't have like an obvious pattern on your residual plot, then your linear equation that you choose here is a good guess. It's a good equation to use. So like when I look at these guys, when I look at these residual plots, and when I'm talking about patterns, right? If I were to look at this and say, look, this guy here represents a linear equation, this represents a linear equation. Is a linear equation appropriate for this? The answer to this guy is no. Since there's a pattern that looks very quadratic going on here, plot 1 does not represent a good linear equation because the pattern is above, 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 below, 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 coming back up, above, above, above. That's a pattern. So is that guy. My lights just went out. Perfect. And no one will ever notice. So that's a pattern too, because it's above, above, above. It looks quadratic. So in cases like plots 1 and 2, these are nonlinear. The residual, or a linear equation does not fit this data. What about you? You might look at that and say, there's no way you're going to talk about all those scattered plots being linear. They are. This is linear. Okay. Now, the reason why this is linear is if you were to pretend that this guy is a line of best fit, these dots are all over the place, which means the linear equation seems to fit the data. Okay, so residual plots are very strange, but what you need to understand is if there's an obvious pattern, you would say that these guys do not fit a linear model. If the pattern is all over the place, like you saw that it was here, you would say that it does fit a pattern, a linear pattern. So now I believe I can get into a bunch of problems. So let's move my face, even though you can barely see it. Let's move my face over there. Let's answer a bunch of problems. Okay, let y of 1 equal f of x. Okay, y of sub 2 equal g of x, and y sub 3 equal the inverse of g of x. Okay, find f of 3. So your f, your g, and your g inverse. F of 3 is 24. Okay, simple. F of g of 2 means that I'm going to start out by going to g of 2. So g of 2 is 10. So g of 2 is 10. So now I need to find out what f of 10 is because g of 2 is 10. F of 10 is 3072. Okay? Find g of g inverse of 5. So here's g, I erased it. G inverse of 5. So here's 5 is 1. So g of 1 is going to be 5. Well, that makes sense. There's a little rule that says that the inverse of an inverse, or f of its own inverse, is going to equal x. So f of f inverse of 5 should be 5. F of f inverse of 8 should be 8, and vice versa, which takes us to this guy right here. Because if you were to go to find out what the g inverse of 7 is, you're going to find out that it's 1.4. So you trying to find out what g of 1.4 is impossible for this problem. However, you know that the function of its inverse is going to be the number that you plug in. So I can bypass all of this because this guy right here is impossible and say that the answer is 7 anyway based off of that rule right there. How exciting. Okay. What the heck am I asking here? Find f of g of 1. All right, let's do that first. This is me asking you this. F of g of 1. So g of 1 is 5. So f of 5 is 96. Okay, I got that. Plus 3 times the inverse g of 10. So that was the inverse. So that's 2 minus 2. So plus 6 minus 2 is plus, what was that, 90? Oh, that's 96. 96 plus 6 minus 2 is going to be a perfect hundo. Oh, man, I don't think I meant for that to happen when I created this problem, but it happened, and look at that. Look at God. I kind of like the lights being out. It creates an ambiance. I should always record these at home, but I don't have time. Consider the two functions, f of x and g of x. Find f of g of 3. All right. So g of 3. G of 3, that's supposed to be a g. G of 3 is going to be 3 squared minus 3 times 3, which is 9 minus 9, which is 0. So f of g of 3 is f of 0. F of 0 is going to be 2 times 0 plus 1, which is 0 plus 1, which is 1. Bang! Now this guy I'm working a little backwards. Now I want g of f of 2. So f of 2 is going to be 2 times 2, which is 4, plus 1 is going to be 5. So I need g of f of 2, which means g of 5. G of 5 is going to be 5 squared minus 3 times 5. So 25 minus 15, which is 10. Determine the domain and range of f of g of x. Well, that means I have to find f of g of x. Now, the way I find f of g of x without plugging in a number is I start out with f, and then what I do is I replace every x with g of x. Start out with f and replace every x with g of x. So f of g of x, f of g of x, I'm using my patriotic colors, is going to be 2 times whatever g of x is plus 1. So g of x is x squared minus 3x. Use a different color. X squared minus 3x. So now it's distributed property. So 2x squared minus 6 x plus 1. And what I'm supposed to do is determine the domain and range of that. So I know that my domain is going to be everything, because this is going to be some type of quadratic opening upwards. It's going to go through 1. So my domain is going to be all real numbers, so I can write that out as negative infinity to positive infinity. My range, what I should have done is I should have put this in my no calculators, or in my calculator section. So whatever the minimum is, and I could probably calculate that out using calculus, but I'm not going to do calculus. I would be very surprised if you'd be asked to do this without the use of a calculator. I created this problem anyway, and that's what I get. So the range is whatever the minimum is, and I'm not going to go above and beyond, whatever the minimum is to infinity. All right, describe f of g of x plus 3. Well, I found f of g of x. So literally just by adding 3, it's not asking me to do a whole lot more than describe it. This is me just moving it up 3 units. That's it. Plus 3, move it up 3 units. So whatever that guy is, up 3 more. Boom. Done. Easy peasy. All right, so let f of x equals 4x minus 6, g of x equals 2x squared plus 1. Find the inverse function of each. Okay, so very similar to what we had at the very beginning. What I'm going to do is I'm going to do f of x here. I'm going to always swap out the f of x with y for the time being. Okay, step number 1, change the x and the y, swap them. Solve for the new y. Add 6 to both sides. Okay, divide everything by 4. Y is going to equal x plus 6 over 4. But the last thing we need to do is don't make it y, make it f. Inverse of x equals y plus 6 over 4. Okay, f inverse. Bada bing. The next guy, not as pleasant, but we saw one very, 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 very similar to the very beginning. In fact, it looks like it's the same thing. I can't imagine me doing that, but maybe I did. We've got y equals 2x squared plus 1. Swap the x and the y. So x equals 2y squared plus 1. Subtract 1, subtract 1. So x minus 1 equals 2y squared. Divide everything by 2. Divide everything by 2. Cross u out. So I have x minus 1 over 2 is going to equal to y squared. In order to solve for the y, you have to square root both sides. Don't forget your plus and minus. So now you have y equals that, but I'm going to write it out as g inverse of x equals positive or negative big square root of x minus 1 over 2. Now, I'm not going to rationalize the function. I'm not going to worry about the fact that there's a 2 on the bottom. I'm going to leave it like that. Sue me. Confirm that f of negative 1 of x equals x. So basically what I have to do is do what they told me. F of means I'm going to start out with u. Okay. I'm going to start out with, so f inverse of x. I'm going to write this out, but instead of x, I'm going to put a big parentheses minus 6. Okay. And instead of x, I'm going to type in inverse. So I got x plus 6 over x. So distributed property, not over x, over 4, over 4, over 4, over 4. That would change a whole lot. That would change a whole lot because I don't need the distributed property at all for that. If I had that case, I could just go like this. So that's going to equal x plus 6 minus 6, which crosses out to x, which is what I'm supposed to get. Confirmed. Find g inverse of f of 3. Well, let's find out what f of 3 is. F of 3 is 4 times 3 minus 6, which is 12, minus 6, which is 6. So f of 3 is 6. So g inverse of 6 is going to have me take this guy and plug it in. Okay, so positive or negative square root of 6 minus 1 over 2 is just going to be the positive or negative square root of 5 over 2. So yeah, I'm going to have, there's not much I could do there. There's not much numerage I can do. So yeah, that's my guy. Not pleasant. But, you know, I did the math, and that's kind of the purpose of this whole thing. Take a look at the residual plots. I'm looking here. Which plot demonstrates an appropriate linear model? Well, what we said at the very beginning is if there appears to be no obvious pattern along this line, that would make it a linear model. So you're a linear model. Well, about you? Well, you look to have this quadratic-looking behavior, which means you're not. So you're linear, you're not. The end. Now we're going to deal with our calculator stuff. Okay, so lots of, not split screens, but I'm going to cut away and come back. Let's try to understand each problem before I do a whole bunch of things. Suppose you're considering investing in a cryptocurrency known as crypto coin. It's like a teacher made this up. You want to model the growth of your investment over time. You record the value of your investment at different time intervals and create the following table of values. Find the equation that models the growth of your investment in crypto coins. So what I have is I have 0, 1, 2, 3, 4 in time and months. And my investment goes from 2,000 to 2,300 to a little bit more extra to a little bit more extra. So it doesn't look linear. So find the equation that models the growth of your investment. Well, first things first, this isn't linear. So since it is an investment and investments tend to grow exponentially, I'm going to use exponential regression for this guy. Take it away. All right, so we are doing a little bit of exponential regression. So let's just fire it up. Stat, edit, 0, 1, 2, 3, 4. No typos, please. Then we've got 2,000. Then we've got 2,300. Then we've got 2,600. Notice that they're increasing and increasing a little bit more every single time. That's what makes it exponential. So it'll be, yeah. I thought I made a typo there, but I didn't. All right, so this is what I'm going to do. I'm going to quit out of this. I'm going to hit stat. I'm going to hit calc. And I'm going to go to exponential regression, which I believe is 0. There it is. I'm going to hit enter. Okay, I'm going to store my regression equation in y sub 1 so I can use it to answer part B. So I'm going to hit vars, go to y vars, function, enter, and then once you hit calculate, you get your equation. So there's my equation right there. Y equals 1998.974, I guess we'll round it to. And that'll be multiplied to 1.151 to the x. All right, so the equation that I got was y equals 1998, the year of my birth, 0.974 times 1.151 to the x, exponential growth. So that's the exponential. Definitely not linear, definitely exponential. Use the equation from part A to predict the value of your investment after 5 months. So I'm going to use that equation. I'm going to be a little cute about it. Okay, and I'm going to plug in 5. So now when I want to use part A to find part B and predict what happens after month 5, since I stored this into y equals, I can go to y equals, there it is, hit graph, there it is. I'm probably not going to see anything. So why don't I do this just so I can see? This is an unnecessary step. But if I second stat plot and turn my plots on, right, I will be able to see the points that I use. So if I do that, and go to zoom stat, I can see my points along with a line that goes through it, the curve that goes through it. Is this a bit too much? Maybe, because what I need to do now is find the value as y equals 5. So second calc, although 5 might not be on here. Let me check my window. Oh no, let me check my x max to 5. Yeah, I probably shouldn't have done that. Let's make it 5.5. Second trace takes me to value. Now I can type in 5, hit enter, and I get that number right there, 4,033.795. What are we talking about? Money here? So let's round this to the nearest cent because that would only make sense. Cents. $4,033.80. And so what I get is $4,033.80. So this crypto coin, I started out with 2,000 and 5 months later I made over 2,000 bucks. Wow. If there's anything I learned from this problem, it's that you can't go wrong with cryptocurrency. Hopefully you're not watching this in the near future and everything is falling apart. A company is examining the growth of its user base over time using that function below. Let P of t be the number of users in t equals days. So users, find the initial number of users when t equals 0. I don't need a calculator, but I'm going to use a calculator. Just take a look. All right, so let's type this in. Y equals, we're just going to type it in right away. 1,000 parentheses 2 point, all those numbers. It looks like a very familiar number, but I'm going to pretend that I don't know what number that is. To the 0.1, that's just a regular one. 0.1, instead of t, we're going to use x. This is an exponential function. Graph, we're not going to see anything. So if I want to change my window, since we kind of start out at the 1,000 territory, if I change my window to like an x min of around 1,000, no. Yes. Maybe change you to, I don't know, 2,000. See what happens. Who knows? Graph. Find the initial number of users when t equals 0. So why don't I just hit second trace, go to value, and type in when t or x equals 0, and I get 1,000. Well, that makes a ton of sense. Because if I were to type in 0 into this initial equation right here, that eliminates all of u, turning u into 1, and 1,000 times 1 is 1,000. So A is pretty simple. So common sense would say, look, if I just plug in 0, u would be 0.1 times 0. So this guy to the 0th power just goes away. So yeah, it is 1,000. No calculator needed, but I used a calculator anyway. I'm going to come up with an exponential function. I have an exponential function. I'm going to use that guy to plug in 5. See what happens. B, use the given exponential function to estimate the number of users after 5 days. Well, T is 5 in this case, so X is 5. So I'm going to hit second calc value. I'm going to plug in 5, enter, and it's going to be 1,648.7, blah, 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 blah. What are we talking about? Users, the number of users. So I'm going to round this off to the nearest user because I couldn't have decimal users. So I'm going to make it 1,649 because it rounds up. Okay. If you said 1,648, I don't think you get punished on AP land, but I'm rounding it up because that's where you're supposed to round. 1,649 users. Again, I'm rounding it to the nearest user because you don't want to have a decimal user. That would be illegal. Somebody was chopped in half. Okay. The company collected data and found that at 3 days, you had 1,500 users. Verify if that data aligns with the exponential model. If not, explain why. The company collected data and found out that at 3 days, they had 1,500 users. Verify if the data aligns with the exponential model. If not, explain why. All right, so let's plug in 3. Trace value 3. And no. So I'm going to say no because it's more like 1,350-ish. So that data that this company collected does not verify. That's a big fat NO on that one. Well, it didn't because we ended up with 1,350 or something along those lines. So this is a big fat no, and it's a big fat no because we were expecting, according to our exponential model, 1,350-ish, but instead this guy says 1,500. That's off. And if you were off by 15, that's one thing. But when you're dealing with 1,500 users and you're off by roughly 10%, that ain't good, so we're going to say a big fat no here. Why? Well, because we were off by about 10%, and that's unacceptable. Unacceptable. All right. Moving my face. Another calculator problem. Marketing team is analyzing 2 competing models to predict sales. So we have ourselves a linear equation. We have ourselves a quadratic equation. Determine the number of units sold according to model A and model B when X equals 50, whatever X means. So not a lot of information for this guy. It looks like we're just plugging and chugging. So I have 2 models here. Sounds like me in college. I'm going to type in both of them. I'm going to type out this linear looking guy, 200x minus 5,000. That's going to be f of x. So I will just remember that y sub 1 is f of x. And model B, g sub x is going to be y sub 2. So that's 0.03x squared, a quadratic, plus 500. All right. Determine the number of units sold according to model A and model B when X equals 0. So I'm going to do this. Rather than typing out, second trace, go to value, I'm going to go to my table. So second table, and I'm going to hit down for a few seconds until I hit 50 right there. So at 50, I get a whopping 5,000 for y sub 1. So that tells us that model A is going to be 5,000, and model B, which is going to be y sub 2, is going to be 575 on the dot. So model A gives us 5,000. No calculator needed for that. I could have just done that. That's not 5,000. If I plug in 50, it is 5,000. Stupid. And then B ended up being, what was it, 575. All right. Which model predicts higher sales at X equals 100? Why? So we're still here. Which model predicts higher sales at Y equals 100? Let's scroll down. Let's scroll down. Let's keep scrolling down. It looks like Y sub 1, which is model A, by quite a bit. And it asks us why. Well, because that one's bigger. I don't know. So let's just say that. Well, when I plug in each, the answer was A, because the number was bigger. Simple. Compare the slopes of the functions at X equals 25. What does this reveal about the growth? Be careful. This is not plug in 25. This is examine the slopes. So you are a linear equation. You are quadratic. Okay, you look like that. You look like that. I have to see what happens at 25 for both of these and compared to the two. And since that's gross, I have a feeling that I'm going to do a lot of calculator manipulation and stuff like that. Have fun. Compare the slopes of the functions at x equals 25. Well, if I hit graph, I get to see both, but I really don't see much of anything. So let me zoom out, zoom 3, enter. There's 1. Zoom 3, enter. So I'm not really seeing a good picture here, not at all. So this is what I want to do. What I want to do is I want to kind of get a really good view of each of these. So I'm going to hit window. I'm going to change. I care about what happens at 25, and I want to compare the slopes. Okay, so let's make this number 20. Let's make you 30. Let's see what picture we get there. There's the one. I still don't even see the other. So what is blue? Blue is the first one. So I'm yet to see the second one. So let's change my window to, I don't know, negative 500 to regular 500. There's one. And I still don't see the other. All right. Well, this is what I do know. Maybe I can't do much, but it looks like at 25 here, the slope is just like a regular positive linear thing. I mean, that makes sense. I mean, at 25, it's linear. So I'm going to keep that and say, yeah, all right, so model A is linear. I'm writing it down. Model B is quadratic. So I'm not sure why I'm having such a hard time viewing model B, except for the fact that it's going to be insanely steep at 25. Okay, so if I zoom out and make my Y max like much bigger, like let's put it at 5,000 and see what happens. Hit graph. It's not insanely steep. I was wrong. Model B is really not steep at all. So I was way off in my prediction there. So what does that reveal about the growth sales of each model? Well, that tells me at that moment right there at 25 that A is growing at a much higher rate than B at that very moment. So I'll say that. So the linear model was much steeper, like significantly steeper at that moment right there. So what that means is model A has a higher, what are we talking about? Sales? A higher sales rate at 25, whatever 25 means. Okay, but since the slope at 25, which is much steeper than the slope at this guy in the quadratic, we could say that the rate is steeper, which means the rate is larger. Last one. Yes. The biggest rivalry of them all, Captain America and Jesus. They're having a debate about this data over here. Captain America thinks the data is linear. And he thinks the equation y equals negative 2/5 x plus 2.3 should do the job. Draw a residual plot to show that Captain America is wrong. Yes, the old battle between Captain America and Jesus. Let's put in our values. Stat edit. We've got 1, 0 through 7, so no typos necessary for that one right there. And then we just type it in, 4.11, 1.87. And what we're supposed to do with this guy is draw a residual plot using the equation that we have. So I'm going to continue typing this out. Oh my gosh. I was hoping to pause it and I didn't. You got a picture of sound of me sneezing. Sneezing so hard I typed out the wrong thing. 'Tis the season. All right. I'm going to leave that in there. Okay. So those are my guys. So this is what I want to do. I want to see them. Okay. Because if I have like a residual plot thing going on, I want to see them. So how do I see them? Well, let's get out of here. Let's go to stat plot and let's hit enter and turn our plot on. Okay, so now I should be able to see those dots right there. Now, I don't care about all this stuff. So how can I just zoom in on what's important? Zoom, stat is zoom 9. There you go. Now, I'm also given this equation right here that I want to graph. Okay, y equals negative 2, that's a minus sign, negative 2 divided by 5x plus 2.3. Yeah, see, now, here's the thing. That's definitely not at all linear. And if you're looking at the residual plot, I'm going to draw a residual plot based off of what I see. And the residual plot is going to have like a dot way above, and then a dot on, and then below, and then below, and then below, and then there, and then above, and then above. And it clearly shows a pattern that appears to be quadratic-ish, or maybe it's exponential. I don't know. But regardless, the residual plot, when I show it, is going to show a pattern, and that's no good. So since Captain America thinks the data is linear, he's wrong, because since this shows, and keep in mind, a residual plot is basically this guy but sideways. Okay, since you have above, on, below, 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 on, above, above, it shows the pattern, which means linear is not an appropriate model. Sorry, Captain America, but just like always, Jesus is right. So give or take, the residual plot is going to look something like this. I mean, obviously it's not exact, but, you know, it ended up looking something like that, which, as you can see, that is a pattern, a quadratic-y looking pattern. So is this linear? Is this data linear? No, this ain't linear. So I'm sorry, Captain America. You might be strong and you might have America's rear end, but not in this one. Not in this one. I censored myself. Jesus says the data is exponential. Use exponential regression to create an equation and compare it to the points on a calculator. Now, what I'm going to do is I'm going to do some stat plot stuff. For me, it's not good enough to just come up with the equation. I want to see the points and see the equation to see how accurate Jesus is. Now, Jesus says the data is exponential. So I'm going to use the exponential regression to create an equation and compare it to the points on the calculator. So I didn't do that yet. So if I quit out of here and I go to stat, calc, and I go down to exponential regression, which is 0, I'll be able to get my equation. But what I also want to do is I want to store it into y equals. So enter, enter, enter. I'm going to hit vars. I'm going to hit window. I'm going to hit, vars. I'm going to hit y vars. I'm going to hit function. I'm going to hit y sub 1. I'm going to calculate it. And that's the equation that I get. So the equation that I get is y equals 3.389 times 0.526 to the x. Now let's graph that. See, I stored it in my y equals, so there it is. Now it covered the old linear equation, but that's okay. I don't need that linear equation anymore. So that, to me, is it perfect? No. But does this appear to be an exponential model? It sure does, because it covers things pretty nicely. So there you have it, exponential. Just like always, Jesus is right. Well, as always, Jesus is spot on. I mean, it wasn't exact, but it was pretty close. And the picture that you saw, I mean, the data lined up quite nicely with this equation that we're writing out right here. So that's the second chunk of Unit 2 in AP Precalculus. Okay, residual plots, composites, inverses, Lots going on here. So yeah. And soon after this, there will be a video coming out. If you're already in the future, the video is out. That has to do with a progress check, part A of Unit 2, which covers the first 8 sections of Chapter 2. But this is only 5 through 8 to give you a nice, just in case your teacher gives you a quiz or something like that. This covers all of that. All right? So there you have it. Thanks for watching. Don't forget to like and subscribe. Give me some of that sweet, sweet YouTube money. I need it. I need it. Thanks. Bye.